Today we'll be explaining the vector equation of a straight line. So let's assume that this is the line that we want to express in terms of vectors. On this line, there are points A and B, each with position vectors A and R. Now it follows that since A and B are on this line, the direction vector is AB. Now with this line, the vector equation would be expressed as R equals A plus lambda AB. And now I'll explain why this is so. So earlier you would have learned about the addition rule, or the triangle rule of vectors, where in a diagram like this, A plus B would equal to C. So if we think about the R on the left-hand side of that equation as a bunch of output coordinates on different points on the line, as shown in this diagram, we can see how we can use the triangle rule of vectors. Because on this bigger diagram, we can see how R is basically the sum of A plus the direction vector A to B. But since that direction vector is scaled, we have a lambda in front, and that's why we have R equals A plus lambda AB, and this is how we get the vector equation of a line. Here, A is the position vector of a known point, AB is a direction vector, and lambda is a scalar. And this is known as the vector form of a line. Next, we'll be doing an example question. So, find the vector equation of a line passing through 1, 2, 3 in parallel to 3, minus 1, and 4. So from this question alone, we can first see that 1, 2, 3 would be the position vector, and 3 minus 1, 4 would be the direction vector. So following the format that we had earlier, we can write the line equals to 1, 2, 3 plus lambda 3 minus 1 and 4. So a follow-up question could be, is the point 7, 0, 11 on the line? So the first thing to do would be to check the x-coordinate. So if we follow the vector equation of the line, we can write that the x-coordinate would equal to 1 plus 3 lambda. If we set that equal to 7 and then solve for lambda, we'll get lambda equals 2. So next we can sub in lambda 2 into the rest of it to see if it lines up with that point. So for example, for the y-coordinate, we can go 2 plus 2 times minus 1, and if we calculate that, that's 0. And for the z-coordinate, if we do 3 plus 2 times 4, we get 11. And 7, 0, 11 is exactly the same as the point, so we can say yes, the point is on the line.
Equation of a line. But this is not the only way to express it. I'll be covering two more ways we can express a vector equation of a line: the parametric form and the Cartesian form. As seen here, this is what they look like. This is the parametric and this is the Cartesian form. So moving on, how do we get parametric equations? So from here, we can see that we can think of a parametric equation essentially as telling us where along a certain axis we are, depending on the value of lambda. So if I want to know where x is, we only need to care about this line of variables. So in this case, it'd be a and x1. So I can rewrite this as x is equal to a plus lambda x1. And we can do that for each axis, giving us this: y equals to b plus lambda y1, and z equals to c plus lambda z1. So how can we use the parametric equations to find our Cartesian equation? Well, essentially, if we notice here, all our parametric equations share the same value, all depend on this value of lambda. So if we want to equate them all, we should isolate lambda. So as we can see here, we want to just isolate lambda to get this. So in the first equation here, I'll be doing x minus a is equal to lambda x1, and therefore x minus a over x1 is equal to lambda. If we do that with all the other equations, we will get this: y minus b over y1 is equal to lambda, and z minus c over z1 is also equal to lambda. Now, since all these equations are equal to lambda, we can now equate them as, now we know that x minus a over x1 must also equal to y minus b over y1, and must also equal to z minus c over z1. And that is how we derive the Cartesian equation of a line. So that is how we can get our three equations of a line. So while it might seem benign to understand how to manipulate these equations to represent them in different forms might be more effective at solving different equations. So it is important to understand these three different methods.
So with our new knowledge of how to convert between different forms of vector equations, we're going to solve a question. So the question is, find the point of intersection between the lines r equals 2i minus 5j plus lambda minus I plus 3j and x plus 2 over 3 equals 1 minus y. And here we can note that they're written in different forms. So the first step would be to rewrite the equations to parametric form. And while I wrote both, I actually mean the first one only. So if we rewrite the first one in terms of vector form first, then we'll get xy equals 2 minus 5 plus lambda minus 1, 3. And that's just sort of a different way of expressing the same vector as in the question. And if we rewrite that to parametric form, then we get x equals 2 minus lambda and y equals minus 5 plus 3 lambda. Next, we can substitute the coordinates as written above into the equation of the second line because we're trying to find the point of intersection, meaning that the coordinates have to work for both lines. All I did was put 2 minus lambda into x, so we get 2 minus lambda plus 2 over 3, and the same for y, so equals 1 minus 5 plus 3 lambda. Next, we solve for lambda, and we get lambda equals 7 over 4. So the last step is to use the parametric equations as written for line 1 to find the point of intersection. So all we do is sub in this new value of lambda into the equations for x and y. So our final answer is 1 over 4 times 1 over 4.
We're all quite familiar in a 2D space what two straight lines can do. As you can see here, they can either intersect, in this case, at this point, or when their slopes are equal, we can see they never intersect and are parallel. So no matter how far we go, these lines will never touch. And again, no matter what the slope is, there will always be an intersecting point, or they will be parallel in a 2D plane. But what does this look like in 3D now? So as you can see here, we have our two sets of line interactions that we know from 2D, which is again parallel. As you can see, these two lines here, they're parallel to each other, so they have the same direction. And again, if we change our value here, no matter what it is, they will still be parallel just because they're facing the same direction. So it doesn't matter where this line is relative to the plane. As long as they face the same direction, they are still considered parallel. And again, we see this other interaction between these two lines where they intersect at A. So this line interaction we have covered before in a 2D plane. As you can see here, these lines intersect at this point A. But finally, an interaction that is new to 3D is called skew, where it is neither intersecting nor parallel. Now to visualize this, I'll bring in a new line here. And as you can see, it doesn't have the same direction as this line that has the point A. As you can see, it's facing this other direction. Yet it passes through the lines without ever touching. And while this might be a hard concept to grasp, if you just take two pencils and do this in real life, you can see how frequent it is that these interactions occur, and it will help visualize how these lines in vector format work. So again, to cover it, there is 3 interactions in a 3D plane between lines. And as you can see here, between this line and this line, you can have them intersecting at a certain point. If I bring my previous line back, we can have them parallel, as you can see, facing the same direction, having the same direction vector. And finally, the new thing we have learned, skew, where it's not parallel, but it doesn't intersect. It kind of passes through, and this is only able to happen in our 3D plane. So that concludes our video for our vector line of equations, and hope that you've learned something.